Welcome, everyone. I'm going to tell you a bit about regional climate models. Going back to basics. So how do climate models work? First, we divide up the Earth into a grid. So here's a schematic representation of what we might do for a global model. And that each of these grid boxes, we apply the laws of physics, basically. So we solve for the movement of air, for the flow of heat, for the movement of water and the transition between different phases of water, for how sunlight is absorbed and reflected, and how the land surface interacts with the atmosphere in the multitudes of ways that the land surface does. So in order to do that, we're solving what are sometimes called the fundamental equations in the climate models. So for conservation of momentum, so essentially the fluid flow of the atmosphere, we're solving the Navier-Stokes equations. Now, these are highly nonlinear partial differential equations. And so in all of the cases here, what we're actually solving is a numerical approximation to the solution for those equations because they can't be solved analytically. Okay, and we're solving it numerically, we're solving it on the grid that we're discretizing our model onto, and we're solving it using finite difference methods. Some of these other things that we care about, so the conservation of mass and the conservation of energy, these are all fundamental physical laws that we make sure our models follow. For the atmosphere, we have an equation of state, which is the ideal gas law. Probably most people are familiar with that. So that links pressure, temperature, and air density in the atmosphere. And of course, we conserve moisture. So we move moisture around and we let it change phase appropriately in the model. So all of these things are what's happening in all climate models. Doesn't matter if they're global or regional, if they have variable resolution or any of that stuff. They're solving all of these equations in the model every time step. So all of those things I've talked about, they essentially are solved on the grid that we discretize our model on. But in every case, whether global or regional, the grid we solve our model on, even for very high resolution models that might be on like kilometer grids, or even for some experiments, we might be getting down to hundreds of meters. There's lots of climate processes happening at scales smaller than our grid. And we need to approximate the impact of those processes on the climate at the scale of the grid. And we do that by having what we call parameterizations for these various processes. And these parameterizations always include some amount of empiricism. Yeah, so none of them are solved from sort of first principles physics. They often lean on physical equations, but then they include some empiricism to do the scaling between the scale the process happens at and the scale of the grid. Okay. Now, the processes that all the models do include what we can see on the screen here. This is a representation of the basic ones in WRF, but all climate models have to include parameterizations for these things. So here, cumulus is referring to deep convection in the model. So cumulus convection. Microphysics is what's happening inside clouds. So the transitions of hydrometeors between different states might be ice, might be water, might be snow, might be hail, might be graupel. Radiation is referring to the absorption and emission of radiation by different constituents of the atmosphere. The PBL, that's the planetary boundary layer. So the evolution of the planetary boundary layer includes turbulence on a range of scales that get as much as sort of scales of several kilometers, and it's a strongly diurnal function. So it's driven by heating at the surface, essentially, and that generates this extra turbulence, and that mixes through the lower troposphere. And that interacts with fluxes from the surface and how the troposphere interacts with the surface. And then we have the land surface, where we care about the distribution of different types of land cover and how vegetation interacts with soil moisture and to produce transpiration, and how the different, types of land cover, how they interact with radiation through the different albedos and emissivities. And so essentially the water and energy budgets and cycles at the land surface within this parameterization. And then you can see how all the parameterizations kind of talk to each other in different ways by sharing different fluxes and states between each other. Okay, so you can imagine that for lots of these things, the scales they're acting at are, like microphysics, these transitions with hydrometeors in clouds are at micrometer scales. So they're never going to be resolved at the scale of our climate models, essentially. So they have to be parameterized in some form. Exactly how they're parameterized can, however, be dependent on the scale of the climate model. So just keep that in mind. Now, I talked about the fundamental parameterizations there, but actually climate models can include many other parameterizations as well. And here's a schematic about trying to show how over time in our climate models, more and more processes have been included. And many of these are essentially included through parameterizations that get added to the model. And um, I'm not going to talk too much about this, but you can see in the most recent times, things like urban parameterizations have been some of the most newest parameterizations added to climate models in general. So even some global models have urban parameterizations in them to try and represent the impact of urban areas, even at the grid scale of a global model, which generally speaking is still one grid is still bigger than the footprint of a city. Okay, so why might we want to use regional climate models? So our global models resolutions are generally sort of 100 to 250 kilometer type resolutions. So this is thinking about, CMIP models where we're doing long simulations to look at climate change questions. Now, there's lots of work being done on this, but a general kind of rule of thumb, you might think of about 8 grid points being needed to capture wave structures. So in the atmosphere, we frequently have waves that generate and propagate in the atmosphere. And if we, given our grid point discretization of our model, we can only capture these waves well when it's something on the order of 8 grid points for one wavelength. Okay, so if we have a model with a 100-kilometer resolution, we can think of structures on the order of 800 kilometers can be resolved by those models. And that's not really enough synoptics. 800 kilometers, you're thinking, if you think about weather maps and you've got high and low pressure systems, and so we've got sort of wave-like structures that go around them or between them, these structures are often have wavelengths that might be on the order of 600 to 1,000 kilometers, something like that. So 800 is going to be in the middle there. So we're going to get synoptics, but maybe they're not resolved as well as we would like. If we get our resolution down to 50 kilometers, so now we're resolving things down to 400 kilometers, which means most of our synoptic things are longer distance, longer scales than that. Models on the order of 50 kilometers better capture the synoptics. Okay, just because of the way we discretize on a grid and the fact that we want to capture these waves. So our regional models, they have higher resolution. Typically these days you might be talking about 10 to 30 kilometers for continental scale regional models. And clearly with our 8 grid points, we're easy with the regional models at those kind of resolutions. So this is true for high resolution global models as well, right? Once they get down to small enough resolutions, they're capturing the synoptics better than the low resolution global models are able to do. And so here's just a schematic to try and think about that. So a simple wave here, a sine wave. If we only had, 4 grid points in a wavelength, what you might get if it lines up perfectly is this just very triangular kind of structure. Doesn't really capture what our wave looks like. And then you can see as we move to the left and we have more grid points, what we're able to capture looks closer and closer to the actual wave that we're trying to represent. Another way to look at it is to look at some examples. So here's some snapshots from global models and corresponding regional models where their resolutions are about 10 times better in the regional model. And so if we look at some of the wave-like structures here, what we can see is that the big pieces of the wave, they look very similar, right? So it seems like the model's no problem with capturing where the high pressure center is and generally the size and shape of it, where the low pressure center is off to the south. They look very similar, but then if you look into details, we see things missing. So we see that the resolution of the regional model allows us to capture the idea that we actually have a trough crossing in the Tasman Sea from sort of New Zealand direction back towards Australia. And south of New Zealand, we actually have a cutoff low. So you can see in the global model, we got something here that looks like, it could develop into that. But in the regional model, we see it already is a cutoff low. Another example, so here again, the large scale structures are very similar. But in this case, the main difference is that the strength of the low, you can see the regional model's able to capture a much stronger low pressure center than the global model is able to capture. And again, that's what we would expect given the resolution of the grid and the ability of a discretized grid to capture waves. So going to better resolution, just by the nature of the way discretization of grids works, means that we are better able to capture wave-like structures in the atmosphere. Okay, so what about the parameterization? So we talked about the fact that we do need parameterizations for a whole bunch of these processes. At GCM resolution, our parameterization is trying to estimate the impact of these very small scale processes at the scale of the grid, right? So for the low resolution GCMs, they're trying to estimate it at the scale of 100 to 250 kilometer type grids. So there's a big scale gap between the scale of the processes and the grid we're trying to represent them on, and where our parameterization is trying to span that big scale gap. As we decrease our resolution, that scale gap we're trying to span decreases, by an order of magnitude. You still need the parameterization. It's still got to do a lot of work. There's still a big difference between, millimeter and micrometer scales to kilometer scales, but it is a smaller gap. So we can reduce some of that uncertainty. And when we get down to convection permitting models on the order of a few kilometers, then we're able to remove a parameterization completely, the cumulus convection parameterization. We don't need that anymore. At a kilometer, we're actually resolving, that is the scale of cumulus clouds. And so we can let the model's dynamics resolve that scale of convection directly. Now, we use the term convection permitting because some of the convection might still be below the kilometer scale, maybe 500-meter scale, something. Maybe we would really need 100-meter to fully resolve sort of deep convection, cumulus convection processes. So we don't call them convection resolving, but we do say they're convection permitting, which is mostly indicating that we no longer are using a cumulus convection parameterization, and we're allowing the model to resolve that convection explicitly at the grid scale. So how do we use regional climate models? So it's important to recognize, and I'm sure we'll do, that the climate system by its very nature is a global system. So you can't just take a piece of the climate system and ignore the rest of the globe. We need to have some information about what's happening in the rest of the globe. And so we do have to start from a global estimate of what's happening in the system. And that can come from a reanalysis if we're trying to model an observed event, or from a global climate model. And then we use our regional model to refine what's happening to high resolution over our given area of interest. So our limited area regional model takes information from the global models at the boundaries of our limited area that we're looking at with the regional model. Okay. We also start our regional model at some point in time, so we need initial conditions to start our regional model, and that's frequently would come from the global model as well. So we'd actually be starting the model with a kind of a low resolution picture of the atmosphere inside our domain, and then we run our model forward in time for some period. Often people refer to this as the spin-up period. That allows the model then to generate the smaller scale details in the various waves in the atmosphere and that kind of thing, before we would start using the model for analysis. So that means that we do have this special process happening at the boundaries of the regional model. So at the lateral boundaries, so if you think about a vertical cross-section through the atmosphere at each of the lateral boundaries of our regional model, then information coming through that boundary concerns temperature and winds and humidity variables. So that's coming from the global model. It's telling us sort of of all the climate on the rest of the globe. This is what's impacting this boundary. And if we're using a model that's not coupled to an ocean model, then we also need information about the sea surface as well to be an input to our regional model. And that is typically how the regional models are used in an atmosphere and land coupled state with the ocean sea surface temperatures as a boundary condition. But we do have more and more coupled with a regional ocean model as well, so we can actually solve it as a fully coupled regional system. Now, the boundary conditions come into the model on the edges here, so you can see, I hope, a little red box in the interior there, and that little zone between our outer edge and that red box which is, varies by model, but might be 5 to 10 rows and columns inside. So this is referred to as the relaxation zone. And in the relaxation zone, some interesting things or non-physical things happen. In this zone, essentially it's a non-physical compromise between the low resolution view of the atmosphere that's coming from our global model on the outer edge and the higher resolution view of the atmosphere, which is what's happening inside the domain from our regional model. And here, I'm just showing a schematic we've just blown up here. We've got a relaxation that in this case is 5 rows and columns deep. And the outermost row or column, which we call here the specified zone, that is information which is exactly coming from the global model. So it is at the resolution, the low resolution that the global model has. Okay, so it's kind of this smoothed out view of what the atmospheric state is. By the time we get to what we've called here zone 2 or model 1, now we're in the part of the model where it's at the resolution of our regional model, everything's being solved at that higher resolution. And from there, further on inside the domain, it's all at our regional model's high resolution. And we've got this relaxation zone between these two. In this case, it's 4 rows or columns deep. And in this zone, there's a non-physical compromise between these resolutions. So essentially what happens is that the regional model is solving in all these relaxation zone area at the resolution of the regional model, but we still want the information from the global model to be propagated into the domain of the regional model. And so we have a relaxation zone where different models use different functions, but it might be a linear compromise between the regional model solution, which is entirely what controls zone 2, and the global model solution, which is entirely what controls zone 1. So in between, we have a linear, basically have these two estimates of the state of the atmosphere, and we take a linear compromise between them, going from the regional model view to the global model view across the relaxation zone. Okay, so you just need to be aware of that. We have this non-physical thing happening at the boundary. It's needed to make sure the information from the global model is propagated into the regional model. But it also means that if you look at a regional model run, you'll often see at the boundary some quite odd looking things, and that's associated with this non-physical compromise that we're doing in that zone. So in practice, when we use these models, when we're doing analysis, we don't use any of the data near the boundaries, and not just the relaxation zone. Typically, we would exclude at least double the relaxation zone from our analysis, probably even more. Yep. So don't be surprised when you look at the outputs for the full domain and you see some oddities at the boundaries. The model is created such that we have this non-physical actions happening at the boundaries there. Okay. So that's how we're dealing with boundary conditions. So what's the difference or what's similar between regional and climate models? Okay, so we already talked a little bit about this. So there's a lot of similarities to global models. Okay, we are solving all the primitive or fundamental equations. So the conservation of mass, momentum, energy, all the stuff that I talked about at the start. We also have the um, uh, so they're solving all of these equations, sorry, on the grid, on the model grid, and so they're coherent in space and time, and they're physically consistent across all the meteorological variables that we're tracking and moving and adjusting in the model. Um, we also have parameterizations for various processes that are too small to be resolved by the grid. Um, so the same kinds of parameterizations that we have in the global models, although these days a lot of them are scale aware. So there'll be some differences in how they operate at regional model scales, grid scales versus global model grid scales. And as I just explained, we are taking information from the global models into the regional model through the boundary. So that does mean, so if our global model has biases and errors, then those biases or errors will be transmitted into the regional model through the boundary. Okay. So the RCM does inherit some biases from the driving global model. But there's also some differences to the global models. So we're using, because the regional models are at higher resolution, all the regional models are using compressible non-hydrostatic equations, whereas most of the global models are at low enough resolutions that they actually use hydrostatic non-compressible estimations. So at the low resolution, that doesn't make much difference, but at the high resolution, it can make quite a bit of difference. So all the models that go to high resolution are all using non-hydrostatic versions of the equations that they're trying to solve. And that includes the very high resolution global models. They have to also use the non-hydrostatic versions. So the RCMs are not self-contained tools, right? They do need information at the boundaries, whereas the GCMs are self-contained tools. And for the RCMs, yeah, we're solving at high resolution, but over a limited area. And we're typically 5 to 10 times higher resolution. But because we're solving on a grid for numerical stability, we also need to solve using a smaller time step. Okay, so as we increase our horizontal resolution, we have to decrease our time step. And so that means for, like a doubling in the horizontal resolution, it's actually might be 4 times more compute power because we've had to halve our time step that we're using as well. So I did mention that, I talked mostly about these sort of 5 primary parameterizations, but there's lots of other parameterizations that can be included in the models. And in regional models, because we're at high resolution, different types of parameterizations are often included, including urban parameterization is pretty common and standard in the regional models for a while. Things like dynamic vegetation, explicit lake parameterizations are often included, but then also other specialized things. So it might include explicit fire spread in the model, or we might include explicit hydrology and river flow and reservoirs in our models. They don't have to. Lots of the regional models have many of these parameterizations as options rather than standard things that you include in a run. So you might have extra steps that you need to include if you want to include any of these things in the setup for your model, if you want to include it in the regional model. But just to be aware that there are lots of other processes that sometimes are included. Okay, so what benefits do we get from using regional models? Well, we get a few for free just because we're using higher resolution grids. I talked about resolving waves in the atmosphere, but at a more basic level, we're solving finite difference equations on the grid, and they have truncation error associated with them. And as your grid size gets smaller, the truncation error gets smaller. So it's a free benefit you get by increasing your grid resolution. You just decrease the error that's inherent in the numerical solution that you're using. We can explicitly represent some small scale processes, and we include better representation of surface fields. So like the topography, the coastline, the land cover types, all that kind of thing is improved because we go to higher resolution. So a little bit more about that. So first we get the improvement in, or the decrease in our error associated with the finite difference equation, often known as truncation error. So here's just the mathematical formula to show this. And so the right-hand side here is our truncation error, and it involves higher and higher orders of our grid spacing. And so the base level of this is related directly to the grid spacing. So essentially, it just shows that, yes, indeed, because we're using a finite difference approximation, we have a truncation error that is directly related to our grid spacing. So as we decrease our grid spacing, we are decreasing this truncation error. We get better representation of smaller scale processes. So things like land sea breezes can be resolved much better by our models when we get to these smaller scales. And so here's just an example. This figure is just showing from observations the time of day where we get the maximum rainfall. We're looking at a couple of the islands in Indonesia here, and you can see that the time of day you get the maximum rainfall over the land, over the islands, is very different to what's happening over the ocean. And that's associated with this generation of land sea breezes that is producing this sort of diurnal cycle in the rainfall in the area. Now, the gap between the islands here is on the order of a couple of tens of kilometers. So you're not resolving any of that in models that are 100-kilometer or 200-kilometer resolutions. We need to be down in the tens of kilometer resolutions even to capture these sort of processes in our models. And we resolve our surface fields a lot better. So in the top row here, you can see the topography by a model that has like 200-kilometer resolution on the left, 50-kilometer resolution in the middle, and 10-kilometer resolution on the right. And you can see that there's quite a big difference as we go down. 50 kilometers not so bad, but the couple of 100 kilometers is quite bad in representing the topography. And on the bottom row, you can see the result in terms of precipitation, and the topography clearly plays quite a strong role in the precipitation in the southeast, and that is not captured at 200 kilometers, but is captured pretty well at 10 kilometers. It's captured somewhat at 50, but clearly not getting the high intensity over the mountain ranges that we see at higher resolution. And so just capturing the surface fields better can help produce improvements in what our models are able to simulate as well. All right, so now I'm going to show a little animation. So this was some work I did with a postdoc a few years ago. We were looking at heat waves over Sydney, and we were running a model at high resolution, actually sub-kilometer, 800-meter resolution. And so this gives you a look at the kinds of things you can capture when we get to these higher resolutions. And hopefully you'll also be able to hear narration by Annette.
My name is Annette Hirsch, and I'm a climate scientist at the ARC Centre of Excellence for Climate Extremes. And my research focuses on understanding how surface conditions influence the atmosphere and what that means for different weather phenomena and climate extremes. Our research was motivated by how urban areas are often hotter than their rural surroundings, a phenomena known as the urban heat island effect. If we want to understand how urban heat islands are affected by coastal breezes, airflows coming from further inland, or weather phenomena like heat waves, and the interaction between these different processes, we need to use atmospheric models that are fit for purpose and can see the complexity of our cities. Our research aimed to do just that and uses Sydney, Australia's largest city, as a test case for our new configuration of the weather and research forecasting model run at a very high resolution of 800 metres with a new urban classification scheme that describes the complexity of Sydney's built environment. Our results show that heat waves often start with a hot continental flow over the Blue Mountains, descending into the Greater Sydney region, and that it gets stuck. This can lead to temperature differences across the city exceeding 15 degrees. The urban environment, on average, adds about 1 degree of heat into the lower atmosphere, but over heatwave periods, this can exceed 10 degrees and also impact the Blue Mountains area as well when sea breezes act to push the heat further inland. The simulations cover a sequence of 5 heat waves over the summer of 2017, allowing us to understand what happens over the build-up, duration and dissipation of each of these events as they occur. Starting from the 7th of January, there is a change in the wind direction from an easterly flow to a southward flow over the ocean. And over the land, there is a change in the wind direction, bringing warming conditions over the area from the west. Here we can see the interaction of these different flows and how variations in their strength influences how the heat is distributed over the coastal land areas. On the 9th of January, a warm flow pushes over the land, followed by some convective activity later in the day, where we see what looks like small explosive pulses in the temperature field. The situation cools down overnight, with the heat returning the following day, which marks the first day of the first heatwave event, where the temperature increases. And the bottom panel, where we can see the atmospheric profile, we see a pulse of heat moving over the region and out over the adjacent coastal ocean area. The heat really kicks in on the 11th of January, where a strong westerly flow brings hot conditions that extend out over the adjacent ocean areas. Later in the day, a strong southerly pushes through, cooling the area down by dispersing the heat. Hot conditions return on the 13th of January, with another strong hot westerly flow heating up the area again, and the temperatures are very hot and red over Sydney. So this first heat wave wasn't a continuous pulse of heat. It built up over the preceding days before peaking on the first day, with the southerly providing temporary relief before the temperatures dramatically rise on the final day, before a southeasterly flow arrives around the 14th of January, where we see the contrast of the opposing southeasterly and westerly flows converging close to the coast, before the southeasterly flow pushes through and we see the whole temperature profile cool off by the 15th of January. This kind of behaviour repeats itself for the other heatwave events. However, the build-up can occur over a very short time period, which is certainly the case for the second heatwave event, which closely follows the first. Here, relatively cooler conditions remain until the 16th of January, where it starts to warm up again over the west and sweeps over the land areas. There is a temporary relief where the temperatures drop slightly before the heat returns on the 17th of January, where a strong hot westerly flow returns over the land, and over the ocean the flow is mostly southward. On the 18th of January, another strong southerly arrives to flush the heat out, where the area looks much cooler, as well as through the atmospheric profile. Over the 20th of January, we see the heat mostly localised over Sydney, starting from the north before travelling south over the city and extending towards Wollongong. This time round, the wind field limits heat being transported west over the Blue Mountains region. And later in the day, a strong southerly arrives to disperse the heat, and this is sustained until the 22nd of January, helping to cool things down. The level of detail we can see from these high-resolution simulations is so high that we can really interrogate the role of local breezes to either enhance or dissipate heat, and this capability is the first step towards building an understanding of how our cities will need to adapt to climate change.
There we go. All right, and I'll finish there.
Awesome. Thanks so much, Jason. That was really interesting. Um, and we've got a few questions now, so I think there's still some time, so
Yep.
we can go through them. Um, let's go through. So the first one we've got is, could you please explain what is the role of the spin-off when the RCM is generated, and why does this happen?
Sorry, can you repeat that? I can't see that here, so.
Oh, okay. I've just got the Slido up.
All right, that's
Um,
fine.
so it's just talking about the spin-off when the RCM is generated, and they're wondering if you can explain the role of that spin-off when you generate the RCM.
The spin up.
Yeah, I guess spin-off, yeah.
Yeah. Okay. Yeah. So the idea here is that when we initialize from the global models, we're essentially starting the original model with a very kind of smooth view of what the atmospheric state is. Okay. And the regional model will impose, or not impose, but will uh, resolve higher um, resolution features in the atmosphere um, as it runs in time. So when you run forward in time, it will start to generate higher resolution features, right? So, so for example, if there was a convection being generated in the global model, that's convection is spread out over, 1 to 200 kilometers, whatever the grid scale was of the global model. Whereas if the same storm or convection was generated in the regional model, maybe it's only contained in 10 or 20 kilometers because multiple grid cells can contain that convection. And so it's a slightly different view of the atmospheric state, even though it's trying to resolve the same phenomena. And it's only because of the change in scale that can be resolved. So the spin up you do for the regional model is essentially to give it a chance to generate these regional scale features, because usually we're not actually doing a study of how the smooth GCM picture of the atmosphere transitions into the high resolution of the regional model. I have done a study like that in the past, so I was very interested in this period. Usually what we're interested in is not that, yeah? So we don't want to include that in our analysis. We don't want to accidentally think it's telling us something about the process of interest, when really it's just telling us about the difference in what is resolved in the atmosphere between the global model that we start with and the regional model and what the regional model can resolve. So typically for when we're doing climate length things, we'll use maybe 3 to 6 months as a spin up that we then won't include in our analysis going forward.
Mm.
Now, it's a bit different when you do weather forecasting because they do data assimilation. So they use the data assimilation process to impose high resolution atmospheric features into the field. Yeah. And so in that case, they really want to minimize any spin up problem with the model, right? Because they want the forecast to be useful from like 1 hour after the model starts. And so that data assimilation is doing a lot of work for weather forecasting.
Mm. Interesting. Um, Sort of on that as well, one person's interested in the empirical aspect used for parameterization. So I guess how observational data included in the parameterization process, and where does this information come from? And if you have an example of that.
Yeah. The developing parameterizations is a bit of a black magic art, I would say. So if you think about the different processes, let's take an example like radiation. Okay, so what we're parameterizing is in the atmosphere is how does radiation interact with the different um, chemical composition of the atmosphere. So all the different chemical species, the nitrogen, the oxygen, carbon dioxide, carbon monoxide, nitrate, nitrous oxide, sorry. Um, but then also, how does it interact with aerosols? How does it interact with different water species? So cloud drops, ice crystals, snow, all that kind of stuff. And so what they do is in the lab, you can make a container of pure oxygen. And then you can shine radiation of different wavelengths through it, and you can measure how it interacts. Okay. And you can do that for all gaseous species. So you have independent estimates, good knowledge on, the emission absorption spectrum of different gas species. It's not so easy for like aerosols. There's like an infinite number or variety of different types of aerosols that can differ slightly, but it does change the way they interact with radiation. Um, they do try to do it with different water species. So they've done the similar kind of lab experiments with different water species. So we have a reasonable idea of that. But then some of them, like the ice crystals, ice crystal structure is different for every ice crystal that forms. They're never identical. I'm sure you've heard that, every snowflake is unique. Um, that is true, and that means there's slight differences in the way they interact with radiation. Of course, if you've got a blizzard, it doesn't really matter that they're unique. The effect is the same. Right. So how you make a parameterization. So we know individually at the lab scale what all these different things do, how they interact with radiation, and then we have to estimate, well, at the scale of a grid, like 100-kilometer square area, we've got a mixture of all these things. So how do we, even though individually we know pretty precisely how each individual thing would react to the radiation, how does this big mixture react overall? And what's the overall effect of all that things in the mixture? Okay, and that's what the parameterization is trying to do. It's trying to do the calculations of the mixture and then tell the model what their overall impact is at the grid scale. Right? So that's for radiation. So radiation is a nice one because actually, at least for the individual components, we can measure really precisely in the lab a lot of what the individual components are doing. Some of the other ones, it's much less clear. So for things like the microphysics in the cloud, while we can understand in the lab, how how cloud droplets might form onto hydrometeor seeds. So, tiny aerosols in the air. Most droplets form on top of the aerosols. If you have very clean air with no aerosols, droplets won't start to form, and we'll get what people refer to as supercooled water. So water can be far below freezing point and not freeze if it doesn't have anything to freeze to. So you can do some lab measurements on stuff like that, but then in real clouds, how do we understand what's going on? Well, people do field experiments, right? And they fly aircraft through the clouds and they drop sondes into the clouds and they're taking direct measurements of the different types of hydrometeors that are there and then trying to take repeat measurements to then get estimates of what kind of transitioning they've got between different hydrometeor species. And it's not a something you can derive from sort of physical first principles. It's all something that is estimated based on these experiments or these measurements that are taking for particular storms in particular places. Now, over time, we've built up a lot of these measurements all around the world for different experiments that have taken place. But in the end, in the models, we're trying to take observations like these, like aircraft observations that flew through a storm. And then we're trying to say, well, at the scale of a 100-kilometer grid cell, maybe the storm is taking up 10 kilometers squared of that. So there's a fractional thing into the storm that's in. And then we have to estimate, based on the vertical level the aircraft was flying through, maybe the storm looks a bit like that, but then it differs at different vertical levels, adjusting by the convection that's happening in the cell and that kind of stuff. So again, we do use observations to inform the development of these parameterizations. But then it's the parameterization has to do the heavy lifting of saying, well, this is based on the obs, we can say this is what's happening at the cloud scale. But then at the grid scale, which for a global model is much bigger than the cloud scale, how do we translate that cloud scale to the grid scale? And so you can see that as we get to higher resolution, so the regional models are operating at closer to cloud scale. So the parameterizations for this are actually derived from observations that are more relevant to the regional model scales. And so it reduces the amount of uncertainty associated with the parameterization because it's actually being applied at the scale of the observations it was based on. Yeah. So that's two of the parameterizations. So every of the parameterization has a story like that. They're all slightly different from each other. There's all have observations involved at their basis, but then they all have a big question on, how you go from the scale of the observations to the scale of the grid. And there's not one way to do it. And that's why you find, there's many different cloud microphysics parameterizations that have been built. And they all are trying to do the same thing. They all do it in slightly different ways, and they'll give you slightly different answers when you use them in a model. And so there's a certain amount of inherent uncertainty in our models because we have to use these somewhat empirical parameterizations to estimate what's happening for these processes at the grid scale.
Thanks very much for that. Yeah.
Can I ask a follow-up to that? So when you talked about the cloud scale to the grid scale, I'm just imagining if you're testing like how, I guess, permeable a cloud is to radiation, like how much radiation gets through the other side, and you've got all these clouds that you've measured that for. Like when you take that from the cloud scale to the grid scale, is there a way of capturing, like, we'll probably have like, I don't know all the cloud types, but we'll have like a thin cloud and then a medium cloud and then a big cloud probably on a grid. And then we'll have that like over maybe 40% of the grid on, I don't know, in May and like 50% in September, or like how, yeah, I'm just trying to imagine, like, if you've got this data that tells you through a cloud that has these types of features, then you expect a certain amount of radiation to get through. How can you, like, I guess, like, what's the sort of thinking behind translating that to the grid level?
Yeah, very good question. So there's lots of different approaches that have been taken. Okay, so there are approaches where people have tried to say, well, actually, for things like radiation, it's really important to know what fraction of your grid cell the cloud is occupying and what fraction is clear sky. So some of the radiation is penetrating very easily through the clear sky portion, and some is being absorbed and reflected by the cloud portion. And so they actually will go to the effort of calculating this separately, estimating the fractional cover, and then combining the two of them to give a grid scale output.
Right. And is the fractional cover would be based on like the temperature? And
so
no?
Yeah, so there's no one way. There's no one way.
Okay.
So they each have their own way of doing it. And it's not, if it were easy to sort of show one way was correct or not, they'd all be using the same way.
Yeah.
It's just, it's really hard to actually, prove one way is correct and another way is incorrect. In what I've seen, most of the work comes out with the less than useful result of, method A works really well under a couple of circumstances, method B works really well on some other circumstances. They both do similarly on a third set of circumstances. And so when you want one method to work well all the time, we're still trying to find that method.
Yeah. Is there, and this is my final question because Joel might also have more. Actually, maybe Joel, if there's more questions from the Slido, you can
Okay.
open first.
Maybe let's just choose one to go with. There's a question there's a few questions actually regarding how you evaluate these RCMs. And is there like a quality control process or like some tests that you do to make sure the RCM is actually adding value and it is more precise than a GCM?
Yeah. So pretty much any of the ways that you can evaluate a GCM, you can evaluate an RCM, right? So you can imagine, taking observed temperatures, observed precipitation, calculating your favorite statistics on the grid between the two, the same way you would do for a GCM. The only difference being that you now have a higher resolution grid, so you can actually resolve smaller scale variations in the field. than you would at it with a GCM. So there's nothing, nothing particularly unique about RCMs in that respect. Maybe until you get down 2 kilometer and higher resolution scales, and then you start to have other issues with gridded observations becoming non-representative of the observations that underpin the grid, which we ignore when we're at lower resolution. So maybe everyone here's used AGCD at some point. So AGCD, it's a gridded observation product, but it's built on station observations, so point observations, a non-uniformly distributed set of points underpin the grid, and then they use a method to put on a grid. The result is that when you look at the grid at small scales, at high resolution, you can actually see the influence of the station distribution, right? So in reality, the real rainfall doesn't care where the station is, right? So in the real rainfall field, there is no influence of the station distribution, but you can see it in the data set. So the data set has some issues there. But when we use it to look at broad scale things, it all gets smoothed away and it's not a problem. When we're at high resolution, we need to start caring about things like that, because that's then going to give you a false evaluation of the model, because you're got to account for these observational errors when you do the evaluation. And the other thing you mentioned was, how do we know if we're adding value to the global model? So the sort of fundamental way you can do that is, you do the same evaluation on the global model and the regional model, and if the regional model is closer to the observations, then we say the regional model's produced a better representation of that precipitation or whatever you're looking at. So that's kind of the simple view of what we can do. And there's been a number of methods that have been developed to quantify the added value. And they always involve some comparison between the global model, the regional model, and observations. Yeah. And even though there's lots of different ways people have actually tried to quantify this, the fundamental thing at the basis is that if the regional model produces a climate field that's closer to the observed climate field, then it's added value. Now, that's the purely kind of statistical evaluation view of added value. There's other views that include things like, well, if we're including processes that aren't in the global model, like we're including an urban parameterization that's actually producing a city, and the global model doesn't have enough resolution to include a city, then we've added value. Yeah. So there's more than just the straight evaluation process that can represent added value, but the straight evaluation process is the one that's probably easiest to understand and to calculate, and there's plenty of literature around that is trying to do exactly that, or does do exactly that. And just by the way, what you find is that regional models don't always add value, right? There's certainly times and places and circumstances where the regional models will not be adding value at all. They might be doing a worse job than the GCM.
Interesting. Okay, cool.
Just a quick question following that explanation. Jason, can you mention some examples of when there is not added value?
Yeah. So if we look at, say, the Cortex Australasia ensemble for Australia, and you look at the precipitation in the monsoonal north in the transition seasons, we don't see added value compared to the CMIP ensemble. Now, keep in mind, in both ensembles, global and regional ensembles, in the monsoonal north, the spread in the simulations is very wide. So it is, when I'm saying that don't add value, the ensembles don't add value, I'm talking about the ensemble mean, but the spread's very wide in both cases. So if you looked at individual models in either ensemble, you may find some of them added value and some do not. What we generally find is that places where you might expect resolving regional scale things would help, generally we find added value. So that's, coastlines, mountain ranges, those kind of areas.
Okay, cool. Yeah, thanks so much, Jason, for a wonderful talk, and thanks everyone for joining and your questions.
I hope people enjoyed the animation.
Yeah.
I always impressed when the southerly comes through and you see the big heat get thrown away by the southerly.
Yeah.
That was cool.
Thank you, Jason.
All right, thanks guys.
Thank you so much.
Thank you.
Have a good day.
All right.